Hi, this video is about one final kinematics equation and using it to solve some word problems. To find this last equation, let's start with the velocity over time graph here. Whenever you have a velocity time graph, if you find the area underneath the curve or the line, then that is actually used to calculate the displacement. The displacement equals the average velocity multiplied by the time. And so in this case, the average velocity is 3, and the time is 5 seconds. And so you can find the area of this rectangle by doing the 3 times 5. That's 3 meters per second times 5 seconds. And that gives you a displacement of 15 meters. So the area under a velocity time graph is equal to an object's displacement. Well, what if the object is accelerating? This is a constant speed, but what if it's moving, getting faster and faster? To do the area under this kind of graph, you split it into two shapes that are easy to find the area of. In this case, we have a rectangle and a triangle. So to find the displacement of an object that's accelerating, we just simply need to first find the area of this first shape, the rectangle, and add that to the area of this triangle. So the area of the first shape is the same as the previous graph. It's going to be this line right here, which in this case is the initial speed of 3 that we started out at, and then multiplied by the time. So the initial speed multiplied by the time is the first area. Now this second triangle graph here is triangle area. The area of a triangle is 1/2 times the base times the height. So in this case, the base is the time, and the height here is actually equal to the increase in the velocity, the change in the velocity. And so we write that as 1/2 base times height, so that's 1/2 times the change in velocity. Rearranging that a little bit, we can do something a little unique here. We know that the change in velocity is also equal to the acceleration times the time. We get that from this equation here by rearranging it, solving for change in velocity. So I'm going to actually substitute out the change in velocity, and I'm going to put acceleration times time here. And I do that on purpose because it allows me to simplify things. I have a time over here already, so I have 2 times, which allows me to change it to time squared. So we have 1/2 at squared as the area of shape 2. Add that to the area of shape 1. This is the displacement for any object that's accelerating. Now, if you look, this equation actually applies to this displacement over here as well, because the acceleration is just 0 over here. So an acceleration of 0 means we get rid of this term altogether, and it's just VIT, which is what we had here. And so this is a general equation. It works for any kind of moving object. It's going to give you the displacement. So let's look at an example of that. A skateboarding turtle cruises at a velocity of 12 meters per second when he arrives at the base of a hill. As the turtle starts climbing the hill, he loses velocity at a uniform rate of 1.2 meters per second per second. Question 1, how fast is the turtle moving after 3.0 seconds? So let's do the guess method here. Start with our given information. We know the starting speed is 12 meters per second. The acceleration is negative 1.2 meters per second per second. It didn't say negative in the problem, but it's saying he's losing velocity, and we're starting out in the positive velocity, so he's going to be having a negative acceleration then. The time is 3 seconds. We're looking for the final velocity. How fast is he moving after 3 seconds pass? So using an equation, we're going to pick an equation that has these pieces in it. We're going to try to solve the puzzle here by finding the right pieces that fit into this equation. We have all 3 of these pieces, so that'll give us our final velocity. Initial velocity plus 1.2 negative times 3. So we subtract that, 12 minus 3.6, 8.4 meters per second is how fast the turtle's going. That makes sense. He's slowing down. He started at 12. He's starting to go up the hill, so he's slowing down. Question 2 says, how far does the turtle actually go in 3.0 seconds? So again, we have the same given information, but this time we're going to look for the displacement. I left off the rest of the letters U, E, S, S, but the unknown here is the displacement. How far does the turtle go? We're going to use that new equation we just derived We have the initial speed times the time. We know both of those, and we also know the acceleration. So putting all those numbers, substituting them in, we have 12 times 3, and then we have 1/2 times negative 1.2. Don't forget the negative. And then 3.0 seconds squared. Don't forget the square. We need to do the square first before we do anything. So we square the 3, it becomes 9 seconds squared. Okay, then we multiply all three of these terms together. 1/2 negative 1.2, 9. That gives us negative 5.4. So 36 from before, minus 5.4 meters, 30.6 meters, rounding that to 31 meters. So the turtle goes 31 meters. All right, so let's look at one more example of a problem that is kind of tricky. I just want to make sure that you've seen all different kinds of problems with kinematics. So this one says a Price is Right contestant drops a Plinko chip to win a prize, and the chip accelerates downward at a uniform rate of negative 5.8 meters per second squared. It falls downward 2.00 meters. How fast is it going at the bottom? So in this case, we have some given information that we have to do a little thinking about. So the acceleration is negative 5.8 meters per second per second. The displacement is 2 meters, but it says downward over here, 2 meters downward. So we need to add in that negative sign to show the direction. It's not always given to us in the problem, so we have to do a little bit of thinking when we put that direction sign in there. And then one piece of info that's kind of hidden or implied is that the starting speed was 0. It says that they dropped the chip. And so anytime you see that word drop, it's like, you're holding it before you drop it, so it's at rest. So the starting speed is 0. So what's the final velocity there? So we need to look for an equation that has these pieces in it. It's got a displacement, it's got acceleration, it's got initial speed. There's no time element, so I know automatically we're going to be using this equation. It's the only one that doesn't have time in it, really, that has these other pieces. So we notice we have some squares here as well. We don't want to forget those. So we substitute in, initial speed is 0, acceleration is negative 5.8 meters per second squared. The displacement is negative 2.00 meters. So you see why the negative signs are important here. It allows us to cancel these out. So we end up with a 23.2 meters squared over second squared. But we have this VF squared. The final velocity is squared, so we need to undo the square. The only way to undo a square is the square root. So we do that to both sides of the equation. That gets rid of our square. The final velocity is plus or minus 4.8 meters per second. Anytime you do a square root on both sides, you have to put the plus or minus because we don't know if this number would have been positive or negative before it got squared. So we have to choose the correct direction. So think about it. The Plinko chip is moving at the end and it's moving down. And so we choose the negative sign to say, okay, it's 4.8 meters per second down. All right, so let's wrap it all up with kinematics with this final board here. And it might just help you to pause the video so that you can make sure that you have some kind of knowledge of these equations. I'm not going to say a whole lot about them except for the equations that are in a blue box up here are just variations of other existing equations. They're rewritten in sometimes more convenient symbols. But these are all of the kinematics equations. This one is from a previous module, but it's also very relevant for us as well. So that's all I've got for you in this video. Remember, everything you have is a gift.